let us begin with any questions. All right, let's go to page 65 in your book, please. Okay, and we are going to start with equation 3.9. So we're at page 65, Bruce, 3.9. We've got the pressure times the specific volume. You remember alpha is specific volume, which is the volume of 1 kilogram of the gas, is equal to RD, which is the gas constant for dry air, times the temperature. And then we're saying, okay, we have the apparent molecular weight, which we've done, which is what equation 3.10 is all about. When we get to 3.11, we are now saying the relationship between the ideal gas constant that's universal, which is R star, and that for the gas, whatever gas we're talking about, we're going to divide by the molecular weight. Now, on the next page, they're going to say, hey, you know what? Equation 3.10, or I'm sorry, 3.9 is going to be exactly the same thing as 3.12, but rather than saying dry air, we're going to say water vapor alone. Okay, what is it with water vapor alone? So in this case, instead of P with the subscript D, we are now looking at E. E is the letter that means vapor pressure. Okay? Now, on the bottom, they talk about John Dalton, and they're going to mention Dalton's law. Now, Dalton's law says, because of partial pressures, the total pressure that do not interact chemically, in other words, there's no gases that are combining with any other gases, and nitrogen and oxygen are, for the most part, fairly non-reactive. I mean, oxygen is very reactive, but not with the other gases in the atmosphere. Carbon dioxide and then argon, which is inert, noble gas. It's going to be the total pressure is equal to the sum of the partial pressures. So E is known as a partial pressure. And this is important. So E is so we sometimes will deal with vapor as being what percentage of the pressure is going to be a result of vapor. But in any case, we now have the specific volume of vapor. So in 3.12, alpha with the subscript of V is the specific volume of vapor. In other words, 1 kilogram. And then we have to know what RV is. And RV is going to be the ideal gas constant for water vapor. Remember, and that's just R star divided by the molecular weight of water vapor. And that RV comes out to 461.51. Then they're just creating this thing. They're just saying, all right, the ratio of the ideal gas constants for dry air and vapor respectively is nothing more than the molecular weights of vapor to dry air. It's the inverse because if you look at how the gas constant is calculated, the molecular weight's in the denominator. And then we're going to know, what is 3 lines? Do you remember what 3 lines means, James?
It was defined.
Is defined as, right? We are talking about what's defined as. So what Greek letter is that guy?
Epsilon?
Mm-hmm. So we're defining this little guy epsilon as being the ratio of those two, which comes out to be 0.622. So we're defining the ratio of epsilon, the molecular weight of dry air to vapor, which is 0.622. Now, I am not going to do this completely here, but I think you should be able to understand what is going on in exercise 3.1. So take a look at that problem. Okay, and what do you see in that problem?
Probably just start with the variables, right?
Oh, I was muted.
Right. So you're trying to figure out the total pressure. So what do you need to find out?
The partial pressures?
Correct. So what you're really saying is that the total pressure is equal to the partial pressure of dry air plus the partial pressure of water vapor. So let me share screen. Let me put in Epic Pen. I'll move you guys over here. And all I'm saying is this, that I've got the total pressure is equal to the pressure of dry air plus E. Okay, so I need to figure out what PD is. Well, PD is 1 over the specific volume of dry air times RD times the temperature.
What page is this on?
This is the bottom of page 66.
Okay, that is what I was looking at then.
And then what did they give you? They gave you the density if air were dry alone, which is 1.275 kilograms per meter cubed. So do you agree that 1 over density is nothing more than the density of dry air? So I know the density, and I know this, and then it says it gives you 0 degrees Celsius, right? Well, what's 0 degrees Celsius? It's 273.2 Kelvin, and it tells you what the pressure of dry air is. And then they do the same thing instead of, so what you're saying is this, instead of this, you just go E, instead of this, you go vapor, and instead of this, you go vapor. And you do the same thing, and you get a value for E. And then all they did was add the two together. So notice vapor pressure, by the way, in the book is 6 millibars approximately at 0 degrees Celsius. So we're talking about a pretty small percentage of the total pressure. Okay, is everybody good with that? You know, there are things in here that we do that are tough. This one is not. I don't think that those 2 pages are tough. Did you do your reading like you were supposed to do?
Mm-hmm.
Did you have any problems in the reading? Yes or no?
I didn't like how they described virtual temperature as a fictitious temperature.
As a what temperature?
A fictitious temperature.
Yeah,
I thought that was a poor choice of words.
that's why I think virtual temperature is a way better thing to put in there. Okay. So I'm going to erase all this. I like the black screen. So now we're going to do virtual temperature. Okay, so what they're saying here is the density of a gas. See, this is the deal. The density of a gas is equal to, and I'm going to skip the next one, it's going to be the partial densities. So that's what this little guy here is going to be called the partial. So the partial densities. So we're adding the partial densities. Now, when you talk about the partial density, notice that in the problem before they said it is you have partial pressures, but the density as though it alone made up everything. So what we're saying is the density is going to be, whoops, let me do it this way. Density is going to be the mass of the dry air plus the mass of the vapor all over the volume. So I'm just looking at exactly how much is actually there over this. Because the gases are together in the same volume, I can put the volume on the bottom, right? So I'm not saying that this gas takes up a different volume. They're all in the same place. That's why the partial densities also work like this. So it says where the partial density is the density that the same mass of dry air would have if it alone occupied all of the volume. Because, now look what it says here. This is interesting. We call the partial densities, because rho is equal to the partial densities added, it might appear that the density of moist air is greater than that of dry air. However, this is not the case because the partial density of vapor is less than the true density of dry air. In other words, the reason this number here would be, I want you to think of it this way, and this is going to be really odd. I want you to think of that as it would have been the partial density of the same amount of dry air plus what other mass would have been there if I hadn't put vapor in its stead, plus other stuff. So this is other dry air. And you remember we talked about the brick, the set of bricks? Did I talk about this? A house full of bricks?
No.
Mm-mm.
Did I talk about this?
No.
No.
So when we dealt with the density of moist air being less, and we've done this, right? We said, well, imagine that I have a 10 by 10 brick cube, and 78 of those bricks were nitrogen, and 21% of those, or 21 bricks were O2, and 1 brick was argon. We're going to skip CO2. So that would be the density of dry air. But if I'm putting water vapor into it, what I have to do is I'm going to create some of these bricks as water vapor. I don't know, blue to make. So let's say 3 bricks are H2O. What that means is I need to lower these amount of bricks by some amount, 3%. So this might be, 77.0, and this might, I don't know, 76.8. You know what I'm saying? I'm trying to get rid of this down, so I'm taking out 3 bricks so that I can substitute them with water vapor. So instead of having this, the extra dry bricks, I'm putting in lower weighted bricks of water vapor, and that makes the total density less. So we already said moist air is going to be less dense than dry air because I have bricks that weigh less out of this 100 brick cube. And when I say 100, I probably mean 1,000, but you know, yeah. 10 by 10 by 10. Does that make sense to you guys?
Yeah.
Mm-hmm.
So
And
MV
so
is
that's what they're saying in that top paragraph on 67. So just because you have this equation up here, don't be confused that the density of dry air plus the density of the vapor is actually less dense than it was all dry air. Because this is, if it alone occupied it, would be more. Now, what they do is they say, all right, well, let's go in here and write down the equation for E, which is vapor pressure, which we already said is the partial density of vapor times RV times T. And the pressure of dry air, likewise, well, and this time I have to use the partial pressure because I'm only dealing with the partial pressure. Because remember, E plus P partial D is the total air pressure. It's going to be the same thing, partial pressure of dry air times the gas constant of dry air times temperature. So I use Dalton's law and I add them together, and when I add them together, I get this. plus rho v partial plus RV times the temperature. But what I want to solve for is the density. So I need to extract out of here the densities. So what they're doing here is look at this equation here. Do you understand what this is? Do you understand how they got this?
Yeah, I think I do. Those are the partial pressures for
Right. So
dry
notice-
air and water vapor respectively.
So this, right, and maybe it would be easy if you said total pressure,
Yeah.
right? Because this is nothing more than solving for this guy. So this is actually equals the total density. Does that make sense? That's this is this. The only difference here is instead of saying, you know, they could have said P D, or sorry, yeah, PD. But what's PD equal to? PD is equal to P minus E. Do you see that up here? Are you following that, Jacob?
Yep.
Everybody else good with that?
Yeah.
Okay, so good. So we get this equation. Now, what we do with this equation, and I'm going to go ahead and I think I can delete stuff this way. I'll do it. It's easier if I do it this way. I'm going to take this equation and I'm going to pull out, oops, I'm going to pull out what?
You can pull out a reciprocal T.
I'm going to pull out 1 over T. And what else did they pull out? They pull out an RD. And they pull out a pressure. Now this requires a little bit of mind tricks.
Would that P in the numerator, is that P total?
Yes. So you could put P total. If that makes you feel better, P
Yeah,
total.
it does.
Okay. So I want to take a look at this equation and I realize, what am I doing? This equation here, now watch what I'm going to do, because I'm going to erase something, is easier if I think of it this way. I'm going to think of it as P total over RD. Let me fix this a little bit better.
Oh, I see what
Now
that
you see why they don't want to put P total in there. P
Yeah,
total over RDT minus E over RDT.
they're refactoring.
Right? So that's really what it is. Now when I pull this out, I'm pulling it out of 3 terms. Well, PT, RDT, that's the same thing. So what I have is 1. Now over here, the RDT is fine, but I have a PT, so what I need to do is have E over PT. And then over here, I have an E. I can take the T out easy, but I need to have an RV, and I don't want an RD, so I'm going to put RD all over RV and I need a PT in the bottom. Okay, you follow that? So what you need to do is you need to check it. Whenever you're doing math like this, check it, multiply through and make sure you get the same thing up here. I get PT RDT, I get PT times, and the PTs go away, so over here I would go away, one there, and I have E over RDT, so I can get rid of that. And over here I have a PT goes away, I have an RD that goes away, and I have an E over RV and T. So I've now checked everything and I'm like, okay, that's the factorial. But now what they did is they took this out, and this is where the mathematics often has several steps that you ought to work out before you do it. So I'm going to take out E over PT from these two terms. So now I have to write it up here. And I'm going to go, how do I want to do it? I'm going to do it this way. Watch this.
PT on top of that, right?
Yes. You see that?
Yeah.
Now, what the book did is they factored out a minus sign. So they, instead of saying positive this, they went minus this. This is positive, and that's minus. Right? Minus E over PT, 1 minus,
Oh, okay.
then what is the ratio of RD to RV? That's epsilon. So the way the book ended up with this is this equation. Okay, so do you see that? Because that, that's just a minus signs that are flipping around. Again, sometimes you want to work this backwards to make sure you see it.
That's 1 minus E at the end, just to be sure. Or what symbol is that at the end there?
Epsilon.
Okay, that's the epsilon. Okay.
And then they're saying, so I want you to think about what this equation is. And what I'm going to do is this. I'm going to go PT, the total pressure, equals rho total times RD times T. If I multiply this through, but then I would have to divide by 1 minus E over PT, 1 minus epsilon. And then I'm going to say, okay, this is what I call TV. Where that is defined as the virtual temperature. Fair enough?
Okay, so that's how we get the virtual temperature.
That's how we are defining the virtual temperature. So notice that they don't say equals that. They're saying we're defining it to be that.
Okay, and then at the bottom it's pressure total is the density times RD times.
Yeah, and really this is total density. So this becomes your ideal gas law. Your ideal gas law from here on out is P equals rho RD TV.
And just for the sake of getting it wrapped in my head fully, what does RD stand for again? I just want to get this really burnt in here.
What do you think it is?
I believe that was I haven't done enough studying this week. I know this, it's just,
Write it down and then say what it is if you can't speak it. Come on, you can do it.
Okay.
I know this.
Look it in the book.
Dry air. Okay, there we go.
Gas constant for dry air.
Oh my goodness.
It's the ideal gas constant for dry air, which we know, right? We've already calculated the value of that.
Yeah, that was what we did like last time, right?
What's the value? 287. 287 what? Nick? 287 what? What's the unit?
The unit for the
For R.
joules per Kelvin kilogram.
Per kilogram. Joules per Kelvin per kilogram.
Okay.
So let's take a look at the virtual temperature. What will the value of the virtual temperature be compared to the temperature? Let's look in the bottom. What is this number always going to be? One minus epsilon is always going to be what?
Number less than 1?
What number? You should know the exact, I mean, you could
Oh,
know.
I'm sorry. 0.622.
No? This 1 minus 0.622.
Oh, I'm sorry.
0.378. So this is always a number less than 1, right? Inside there. It's 1 minus, and then what is the value of E over the total pressure? This is always going to be what?
A fraction.
This is always going to be a fraction. And it's going to be relatively what?
Small.
In the atmosphere. Isn't this going to be relatively small?
Right.
So, I mean, this is going to be like parts per, almost a parts per 1,000, right? 3 millibars over 1,000 millibars.
Right.
So this is a very small number times a very small number This is 1 minus a very small number. Makes this close to 1,
Close to 1, right,
but less than 1,
right.
which means this value with the denominator less than 1 is going to be slightly more than.
Right. So in essence, TV varies with T.
Correct.
It's always going to be just a little bit lower.
The virtual temperature will always be a little bit higher
It'll
Higher.
always be a little bit higher. Okay.
because it's in the denominator.
Which is
Oh,
what,
okay,
which is what you see on the skew T.
Exactly.
Yeah, so T in this case is the environmental temperature on the skew T, right?
Yes, this is the actual measured temperature.
Okay,
This is what your thermometer is reading because the thermometer doesn't care. That's why this is a fake temperature. We're just saying we'll increase the temperature to account for the fact that moist air is less dense. But I don't want to deal with always changing the density. Well, actually, I don't care that the density is less. I don't always want to change the ideal gas law depending on the percentage of how much water vapor is in the air. So that's the benefit, is to keep this the same number. It's a lot easier to change it here than it is to go through and figure out what percentage of the air is and what's the apparent molecular weight of whatever that air is.
That would be confusing and tedious to do every time.
Confusing and very tedious. So in other words, let me say it here so you have it on video, and you can take this down. I'd rather change the temperature by a simple equation based on a water vapor measurement than to sit there and have to recalculate the apparent molecular weight of the air with varying amounts of water vapor and then using a different ideal gas constant. Now, I want to jump ahead to page 79 because we've already done this in my classes. We already know what mixing ratio is. So go to page 80. And we can do this little page here. There's no reason for us not to deal with it now, as long as we're talking about virtual temperature, so we have some more practicality to it, okay? So any questions at this point?
Can you just repeat one more time the why we use TV over instead of...
I don't need to repeat it. You go back into the lecture and get it.
Where's the
That's the joy of doing it this way. Sorry, saving time. But does that make sense, James? It's in here.
Yeah. 34 minutes.
Okay, so we have the mixing ratio. Mixing ratio is W, and we're defining it to be the mass of the vapor divided by the mass of the dry air. That's why this is going to be in, what's the unit for mass of vapor? Kilograms.
kilograms.
What's the unit for dry air? Kilograms. We don't like that because this is a very small number. This is like 1 in 1,000. So instead of doing if we said 0.001, we're saying there's 1 kilogram for 1,000 grams of vapor. That's 0.001. So instead we go, let's use grams per kilogram, and this makes it 1 gram per kilogram. So we always multiply it by 1,000 to get numbers that are easier to deal with. So we use grams per kilogram. And it says there in the paragraph on page 80, it says, in the atmosphere, the magnitude of W is from a few grams per kilogram in the mid-latitudes to values of around 20 grams per kilogram. So when you look at your thermodynamic diagram, you are basically looking at values that are going to be somewhat less than 20. Now, because this is a class where I'm requiring that you understand things, let's go to, where can I find this? I think I can find it here, easiest way. Oops, academics, classes and notes. I want to go to severe and unusual weather, and I want to do a thermodynamic diagram. Okay, so you should know how to read. This is called, what kind of diagram is this?
Skew T?
No,
Oh,
this one is a Stufe. That's what this is called.
Stufe.
And I've had arguments with Ron and Mike and blah, 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 but I've taught longer than they have, and I know bad students. Here's what happens. We tend to want to have pressures, temperatures, and which way do our temperature lines go? Temperature lines go up, right? So if I were to look at a temperature that goes this way, what do we say that temperature is doing? It's getting colder with height. What's that doing? It's getting warmer as you go higher. That's an inversion. Very easy to see temperature lapse rates in here. But in a skew T, we are skewing it. So skew T isotherms look like this. So an isotherm is this way. Oops, isotherm. So in other words, on this line, and I think you guys have done this before, dt dz equals 0 on that line. So what is this? What's the temperature doing with height with this line here? Oops.
That would be getting warmer with height then?
Yeah, this is an inversion, right? What is this?
Constant.
No, this is constant. What's this? This is the temperature decreasing with height. Do you understand that this line here is temperature decreasing with height? It is skewed. You have to think about what the values of the lines are. And it's hard enough for you guys who've done this and maybe understand it. Imagine a kid who's brand new that knows very little about graphs is trying to figure all this stuff out. I just don't see that they do that very well. In this case, what are the green lines here? What are those lines called, the green lines?
I might be wrong, but are they isodrosotherms?
No, that would be temperature because it's still a dew point. Those are just constant mixing ratio lines. And to be honest with you, I don't think there's a name for it. It's just a line of constant mixing ratio. Okay, so that's what these green lines are. The thing is, they go through, do you understand that they go through temperatures and pressures? These lines go through temperatures and pressures. So at 10 degrees Celsius, 1,000 millibars of pressure, then there's the line that goes through it. What's the value of this line? 8 grams per kilogram. So do you see that this is 8 grams per kilogram, the value of that line? If this is temperature, this is W sub S. If this is the dew point, then that's W. This should be review for all of you. I think you've all had severe. Jim, you've had severe, haven't you?
Yes, I recognize this.
No, Jim Norris.
Oh.
Yes.
Okay, so all of you should have had this information.
Except me.
Just remembering that. So what I'm basically saying is at 1,000 millibars of pressure, if I have a temperature here, a dew point temperature of 24. Now, what temperature is that? That's like a dew point of 75 Fahrenheit, right? Something around there. Then we're talking about 20 grams of vapor per kilogram of dry air. That's how much the mixing ratio is. That's a high dew point at 1,000 millibars. Now, could you have a dew point of, like, I think the highest is around 86 that I've seen in the United States. So what does that tell me? It tells me that there is about 28 grams per kilogram of air. When the dew point's 80, at a record value, that's how much water vapor is in the air. So that's going to be your maximum amount for the virtual temperature change, 28 grams per kilogram. But do you understand in the book they say it's a few grams per kilogram in the mid-latitudes to maybe 20 in the tropics. So a lot of times when you go SPC, they will use the values of these lines. They will say, okay, well, here we're at 10, here we're at 15 grams per kilogram. Why would I rather use grams per kilogram to tell me how much water vapor is rather than the dew point?
I believe it has something to do with the fact that dew point doesn't actually necessarily tell you how much water vapor is in the air.
What does it vary depending on?
It varies depending on the capacity of the air.
No.
Or not the temperature, right?
No.
Okay, I remember this somewhat, but
Anybody else? The dew point doesn't tell you how much there is. W tells you how much there is. It changes depending on the pressure, right? So if I'm on the Gulf Coast, that's one thing. But if I'm sitting there and I'm up at Denver, Colorado, right? Let's take a look here. Denver, Colorado, sitting at about 850 millibars. So watch this. And I said the dew point's 52. Well, that's like being at 1,000 millibars and the dew point's 58. Or if I said the dew point's 61, that's like sitting at 1,000 millibars saying the dew point's 68. So notice, in high terrain, the mixing ratio may be much higher than you think because the dew point drops with a drop in pressure. Do you remember what the dew point lapse rate is?
that one, no.
For some reason I'm thinking like 2 degrees per kilometer.
That is correct. 2 degrees Celsius. So that's the slope of these mixing ratio lines. So that's why SPC will say, well, I'll just use, here's a mean mixing ratio. Here's what the mixing ratio is, because that tells us exactly where we are. Remember, to find the LCL, how do we find the LCL? We take temperature, go up dry adiabatically. We take dew point and go up a mixing ratio line. There's your LCL. And as a result, that is always going to be a better indication of the moisture values. Now, one other thing we should probably look at is if I were to go to analysis, let's look at this. Let's look at a sounding. Take one in Mississippi because it's raining there. Here's a skew T. You know what? Let's go someplace different. Let's go up here. Sorry, I just think it might be better if I went like this. Here. Here's how you do the mixing ratio line. You have to go up a mixing ratio line from the surface dew point, but the mixing ratio lines on a skew T go this way. And the temperature lines go this way. And this, don't forget, this is a 12Z, so this is not really an appropriate sounding. Why does it keep giving me 12Z? Oh, this is what I wanted. Because it keeps mixing the temperature. That's just the way, you have to understand that you're taking a mixed parcel. But notice that the LCL for a skew T is going to be this. You can take the temperature line, the dry adiabats are still basically this way. The mixing ratio lines are going to be different. They're going to go up that way, though, as opposed to this. They're going up that way. There's another thing about mixing ratio lines, about isotropes, dry adiabats. Notice that the dry adiabat goes up this way, but it curves. You see the way there's a curve in the dry adiabat? On the Stuva, they're pretty much straight. This one, they're curved. Just be aware of that.
Which one do you prefer to use?
To me, a Stuva is more rational, but the lines become closer together. Because here, let me see if I can explain to you why a Stuva is usually used. This, on a Stuva, this is an isotherm. This is a dry adiabat. We've got this much different between 0 degrees and 10 degrees Celsius per kilometer. On a SKU-T, this is an isotherm. This is a dry adiabat. So we can see differences in lapse rates quite a bit better. It's a greater angle so that you have a greater drop down. And also notice that these, if I look at this, do you see how the temperature and the dew point kind of fall into this range? They go almost straight up and down, as opposed to what it would be if I were in a Stuva, which goes way off to the left. Does it matter which one you use? No. You just should know how to interpret it. It's like saying which is better, Fahrenheit or Celsius. Well, it depends. Depends on what I want to know. If I want to know precision of temperature, Fahrenheit's a lot better for at the surface. 72 versus 73 is different by a more specific area. But if I want to do higher atmosphere, I do lapse rates, I do Celsius. So you should know both. All right, back to the drawing board. Let's erase all that. Let's go back to our chart. And now we go to this thing called specific humidity. Now notice specific humidity is a little bit different. So the first thing we're going to say is, all right, specific humidity is Q, and we're going to define it as the mass of the vapor divided by the total mass. Notice this is different. And this becomes slightly different. Now, how do I go from here to here? How does that happen? What can I multiply that doesn't change anything? Those of you who've taken me for intro should know this. What can I multiply by that doesn't change anything?
1.
And what does 1 look like in this case, right? So, and I make a big deal of this because in science, this is kind of important. Any number is equal to 1 times itself. That's the identity property of multiplication, which to a second grader or a third grader, which is when they teach it, is stupid. I always get crazy about that. I'm like, why are you teaching the kids this? Have them do, not, this is silly. But over here, it makes more sense. So what if I multiply by 1 over the mass of dry air all over 1 over the mass of dry air? What do I have in the top?
Mixing ratio, W.
Right, I just have the mixing ratio in the top. And then over here, I've got, I multiply it by parentheses. So 1 over MD times MV is going to be W. and then 1 over md is 1. So this should fall out fairly straightforward that that's how you get this. So it's a little bit different. It's still an exact amount of vapor. It's just relative to something a little bit different. So if you recall, when I define mixing ratio in my classes, I say, all right, take a box of air. And in the box, there's vapor and there's dry air. And I said, imagine that I could take out all the vapor and weigh it. That's MV. What's left?
V.
What's left is MD. Just dry air. Not as much, right? There's not as much mass in there. So specific humidity says, okay, what percentage of the total mass is vapor? Right? This is more of a percentage, which is why it's called specific humidity. Because it is a percentage. Mass of the vapor, of the total mass of the air. Because the magnitude of W is only a few percent, it follows that the numerical values of W and Q are nearly equivalent, so it's not that much different. A lot of times you will see people in science using this, which is fine. As long as you know how you go from one to the other, you're in good shape. So now the next part says, all right, now we're going to do an exercise. And we calculate the vapor pressure, knowing the mixing ratio. Now, do you understand, how do I know W? How do I know W? Like if I said, hey, tell me what the mixing ratio of the air is. What do you need to be told?
Either
Temperature and pressure?
some of the masses. Either.
No. I mean, I'm talking in real life.
Oh.
What did you say, James?
Temperature and pressure?
No,
Sorry, dew point and pressure.
the dew point and pressure. Do you agree? This is always something that's measured. What measures pressure? What instrument?
Barometer.
What measures dew point?
With bulb?
Well, I could use a wet bulb, right, and convert it over, but it's the hygrometer. So there's actually an instrument that measures dew point directly. It's called the hygrometer. So if I know that, I can always use these charts. And a thermodynamic diagram is nothing more than lines based on equations, but I can always get W. So W is easily calculable. I can calculate W very easily from this measurement. Now, if I knew W, I could measure specific humidity, but why bother? So I know W. Okay, so now I'm going to go in here and I'm going to redo this and I'm going to say, all right, so what is the vapor pressure if I know these things? Well, vapor pressure is NV over ND plus NV times the pressure. Now, what does that mean? What are NV and ND? What does little n mean?
Moles. Moles of water vapor and moles of dry air.
So when you see moles, what are you basically telling me? Like when you have to rely on the expression of moles, what are you basically telling me? Nick?
10 to the, or what was it, like 6.23 times 10 to the 23 molecules of.
Yeah, okay, right. So in other words, when you're given moles, you're saying me how many molecules. Now,
Mhm.
I've often said the density is the mass over the volume. But do you agree I could have said it's the number of molecules divided by the volume? So how is mass and molecules, how are they related? Well, I would have to multiply by the molecular weight to get to mass. I'm multiplying by capital M, right? Does that make sense? Because if I know the molecular weight times the number of molecules, I should get you a kilogram. So that's all they're doing here, is they're saying, all right, here's a percentage. Here's the number of molecules of vapor. Here's the total number of molecules. Do you see that this becomes a what?
Small
Isn't that
number.
a part of the total? Or a percentage?
It's a ratio. Yeah. Okay.
Right? It's basically what a percentage is. It's a part of the total. So I'm saying that part of the pressure is a result of vapor. And what part depends on the number of molecules. Now, the number of molecules, NV, is nothing more than the mass of the vapor divided by the molecular weight of the vapor. And then you do the same thing in the bottom. You go, it's just the mass of dry air times the molecular weight of dry air plus the mass of the vapor divided by the molecular weight of the vapor times the pressure. Now, what is this? How do I go from 358 to 359?
You had one?
No.
No.
Right, so look at equation 358 and go to
Oh.
equation 359. Now this is an old Chuck Doswell thing. Chuck Doswell said when he was an undergrad, he was just okay. He was not the smartest. You guys all know who Chuck Doswell is? How many of you know who when I talk about Chuck Doswell? How about the rest of you guys?
We're getting old, Paul.
Chuck Doswell is one of the most influential people in my professional career. Chuck Doswell, Al Mohler are the two people who impacted me the most. There was a time back in, the early 90s, maybe, mid-90s, when the very first storm chase we ever went on, it was kind of weird. We were chasing at the end of March because we went over spring break. And we stopped at the Weather Service office in Norman, Oklahoma. This is before SPC was in Norman, so it's just the Weather Service. There was snow on the ground. This is not good for severe weather, I'm just saying. But we set up a tour, we went in there, and Chuck Doswell is one of the people in the office, and he kind of takes a liking to us. A couple of years later, I had him come out to COD to give a talk and to give some stuff. And so he comes in there and he starts teaching about helicity and shear and stuff to my severe weather class. And I was like, wow, this is cool. Everybody leaves, and now he starts teaching me. I'm sitting in my second row of my classroom, and Chuck Doswell is at the chalkboard writing stuff out. And he started turning to me and goes, and what's the answer? Talk about intimidating. Chuck's very intimidating. He's one of the most intimidating meteorologists that's ever been.
Especially
And
in
he told me a long time ago, never back down. If you don't know something, try something. Don't just sit there and go, I don't know. He hates that. He's like, try it, be wrong. He'll yell at you and then he'll scream and then he'll tell you the right answer. But he wants you engaged. And that made a big difference in my life. And it was so much fun, and I really liked this. So his thing is, he was not a very good student as an undergrad. When he went to grad school, he decided he's going to have to change his life. So what he did is, on every single assignment, he proved every equation. He did the work himself. So that is what you have to do with this problem to go from 358 to 359. You need to do the work yourself.
Well, I know you're probably going to want to start with at least 1 over the mass of dry air over 1 over the mass of dry air. So
Why
you multiply.
do you think that?
Because, well, you know that you have the mixing ratio right there.
Okay, so I've got to get to, so I know that in the numerator, I'm going to need to get to W, right? That's what I'm supposed to get. That's what it is in 359. And that's going to be the mass of the vapor divided by the mass of the dry air. Right?
Mm-hmm.
That's W. But then what else do I have in there?
You have the molecular weight that you have to worry about.
So how about if I get rid of it? If I multiply this times that, do I get W?
Yeah.
But then, and these would go, I can't just cancel them out, right? I'm trying to get rid of them. But if I put this in the numerator, I also have to put this in the denominator. So in the numerator, I get these cancel out and I'm left with W. So then I've got E equals W in the numerator. And now put this in the denominator. What happens to this term?
It's going to be 1 over the molecular weight of dry and
Not 1, right? I'm multiplying this yellow guy times this blue guy. The mass of the dry air cancels out, right?
Mm-hmm.
Over there. And what do I have? I have the ratio of the molecular weight of vapor to the molecular weight of dry air. Right?
Mm-hmm.
Then what's the right side?
That's going to be the
Well,
mixing
those
ratio.
cancel, right?
Mm-hmm.
And that's just back to W. But what is the molecular weight of vapor to molecular weight of dry air? Go look at it. Go back to the page that we left before.
It's that epsilon, which is that 0.
Right? That's
or
epsilon.
0.622.
So you'd say from equation 3.14, if you're going to write up good notes, you go from equation 3.14, this is equal to epsilon. So what I get is W all over W plus epsilon times the pressure. And all they did was switch these two terms. They switched the sign. That's it. So, do you understand this is something you measure? This is a constant, and the mixing ratio is an easy calculable term that a lot of times you're told the mixing ratio. And you plug that in, and now you know the vapor pressure. You know what the vapor pressure is. And then they do it. They substitute in there, and they get E is 9 hectopascals. And what's another way of saying hectopascal?
Millibars.
Millibar. Now, they're going to ask you what the virtual temperature is. Given the temperature with a certain mixing ratio. So now what they do is they go, all right, so I'm going to take this, I'm going to erase this so I can have a new whiteboard. And I'm going to go, all right, let's think about this for a second. By the way, I'm going to do this just because it's fun. It says substituting E over P from equation 359. Do you agree that the ratio of E over P is W over W plus epsilon? Into 3.16. So what do? So this is, so in your notes, you should put something like this is 3.59, and then this is 3.16. So when you're doing notes, you should sit there and go, all right, what is equation 3.16? And you go back and it says, oh, it's the whole definition of the virtual temperature. So you write it out, equals T all over 1 minus E over P times 1 minus, 1 minus epsilon. And we're like, oh, well, that's easy enough to substitute in there. We go T all over 1 minus W over W plus epsilon times 1 minus epsilon. And then what do you do on this? How do you deal with this mess? They said simplify. All right, so what, I see this and I go, well, how do I simplify this? This is crazy. How do I simplify that? What's the best way to simplify it? Multiply it through, right?
Yeah.
So I get W over W plus epsilon minus a minus, so it's plus epsilon W all over W plus epsilon. What do I have? What do I have in both of these fractions? I have W plus epsilon.
You get common denominator, so you can combine them.
Can I combine this guy too?
Yes, you can convert it to 1 plus epsilon over 1 plus epsilon.
No, I don't think I want to do that. I think I'm going to do T all over W plus epsilon minus W plus epsilon W all over W plus epsilon. So in other words, what did I do? I took 1 and I made 1 W plus epsilon over W plus epsilon. And in doing this, I get W minus W.
Okay.
Right? And then that says, well, that's going to be equal to T all over epsilon plus epsilon W all over W plus epsilon. But what can I do then? I can bring the W plus epsilon up in top, so I get temperature times W plus epsilon all over E, or epsilon plus epsilon W. But can I factor out an epsilon? And I go there and I'm like, oh, there we go. There's the next equation. I did it. Isn't science fun?
Whoa.
It's more algebra.
Well, it's a ton of algebra. The calculus, as you'll see in this class, the calculus we do is actually fairly straightforward. It's the high level of algebra that becomes a pain in the butt. But you know how you get better at it?
Practice, practice, practice.
That's right. You just do it. So now I'm going to go to this thing. And I'm saying, okay, the virtual temperature is equal to the temperature times W plus epsilon all over epsilon times 1 plus W. And then it says to divide the denominator into the numerator in this expression, and neglecting terms of W squared and higher orders of W, we obtain this. What? What the hell are we doing? So, try it. See what you get. I'm going to go get another cup of coffee while you're working on this, because I'm the professor and you're not. What do you think, Bruce? Is that kind of mean to say that?
It's ugly.
So try to do what they just said. Dividing the denominator into the numerator. How's it coming? What do you have? Talk to me.
Um,
Are you able to do anything? What do you? Okay, hold on. Who's going to share their screen? Do you have it on your computer, or are you doing it by hand?
I'm doing it by hand.
Well, then you can just show it. What do you have? What did you start doing, James?
I honestly didn't know what we were supposed to be doing. I don't think I caught it.
Nick, what did you start doing?
I'm trying to kind of look at the denominator first and kind of see what I'm gonna have to. I think I'm gonna have to do like the multiply by 1 trick. So I want to figure out a way to cancel.
No,
one.
that's not true. Look what it says. Look what it says to do on the second column of page 80.
Dividing the denominator.
So I'm sorry.
Oh, I goofed. I see.
What are they doing? Having you do? They're just making you do division.
Yes.
Mhm.
Okay.
So
I see.
all I'm really doing, and I'm not. Notice at the end, do you see that there's still an epsilon in it? So I don't really care about that. So what I'm going to do is this.
Pardon me.
I'm going to not worry about this, and I'm going to take this, and for the hell of it, I'm just going to get rid of it and do it again. So what am I doing? I am taking W plus epsilon all over 1 plus W. And I'm dividing it. Now, how do I divide? Isn't that how you divide?
Yeah.
Unless you're flipping, what's the stupid Common Core math? You don't know how to divide anymore? Is this the way you still divide? How many times does 1 plus W go into W plus epsilon?
W.
Okay. W plus 1, or times 1, is W, plus W times W, which is W squared. And then what do? I subtract it.
Subtract.
So what's W minus W?
0.
Epsilon minus W squared. How many times does 1 plus W go into this? What do? Well, epsilon. Epsilon times 1 is epsilon plus epsilon times W squared. Subtract. Epsilon minus epsilon is 0 minus W squared minus epsilon W squared. How many times does 1 plus W go into W minus W squared? Minus what? W squared times. So I multiply it through, I get W squared minus W squared minus W cubed. And what do I get when I subtract the two? These go away, I go to 0 minus epsilon W squared minus a minus is plus W cubed. Okay, so the more I do this, what's going to happen to W?
It's going to get a higher and higher exponent.
Higher exponent. That's called higher order term.
Higher order term, right. Wait a minute.
What?
In your second, when you're multiplying by epsilon, shouldn't that be epsilon plus epsilon W, not epsilon W squared? Yeah.
Yes.
Aha.
Nice catch, my friend. And then you just keep going on, right? You just keep going on. But here's what I want you to see.
Wait, yeah.
Over here, anytime we're dealing with a square term of W. Now, do you agree that W, even at its highest amount, W is on the order of magnitude of around 10 to the minus 2, because we're talking 20 grams per kilogram is actually 0.02 kilograms per kilogram. So I'm taking a small number and I'm squaring it, and what do I get? Even smaller, right? 0.0004. These are really, really small, so I'm going to neglect them. So I neglect higher order terms. Oh, you know what, Jim? Here, hold on. You guys watch this very carefully, because what I did was I carried on a mistake. I had epsilon minus W. How many times does 1 plus W go into epsilon plus epsilon?
Epsilon.
Right, it goes in there epsilon times. And then I'm left with, that goes away. I'm going with W epsilon plus W to the third. How many times does 1 go into minus epsilon W times? Okay. So this is the problem when I'm going without notes, is I make a mistake and then it carries out through there. So what are you going to have to do?
Tutors.
You're going to have to kind of do it yourself. What should you end up coming with? What does this end up being? Look at page 80.
$360.
See, this is a real pain in the butt. So let me do this. Let's do this again. 1 plus W.
Don't you hate textbooks that do this?
Oh yeah.
It's so important, but that they just gloss over it.
W plus W squared. Subtract 0 plus epsilon minus W squared. Then that goes in there plus epsilon. So this is going to be epsilon plus epsilon W minus, so these go away, and I'm left with minus W squared and minus epsilon W. So I'm going to put that up front. And the reason is because then 1 goes into there epsilon W times, times 1 minus epsilon W. But I can't minus, a minus sign is plus. This is going to be what? Minus sign. Times minus epsilon W squared. Subtract 0, then you're going to get minus W squared plus epsilon W squared. And now everything past that's going to be squared terms. So I can stop right here. So this breaks up into W plus epsilon minus epsilon W. But Oops. So now we have to put back into this equation. Let's see if this works. I'm trying to do this without checking my notes. I haven't used my notes in a long time, but I haven't taught this course in a long time either. I'll do it this way just for this time being. Oh no. I need to run to my office for something. Oh wait, that's too far away. So, how do I get unstuck? Look at the next equation. Let's go back. Let's see if we can go backwards. What do I have to have on one side? T. Because I subtract T and I still have T. So I need to get a 1. I need to get 1 over here someplace on this side. So how do I get 1? T, oh, here, maybe this will do it. T times W plus T times epsilon minus T epsilon W. But I also have let's see if this works. I'm just guessing here. I don't have my notes with me. This is bad.
and then divide by W. If you divide by W there, then you get T standing alone and you can subtract it out.
I can't divide by W. I need to factor out a W. Well, this sucks. So now all of us are going to have to figure this one out.
Can you subtract T from both sides up higher?
Now, in order to get this T, I need to do one. I fear that maybe I did something wrong in here. So let me go and let's just try this again. Oops. I know this comes out, and I've done this a couple of times, but I usually check my notebook just to make sure I get the right thing. This is, by the way, this is called synthetic division. Let's just try this part again, because I get sloppy after a while. Let's try this. I don't know if this is going to work. What if I do?
So what I think the author is saying is neglecting W2 in higher orders, meaning the remainder you get to throw on the floor.
I think this might be it. Right here.
Plus,
I'm not sure if this is right.
minus 1. 1 over W.
No, I'm going back and forth, aren't I? 0.
But that's, wait a minute. Multiply by W, that gets W over E plus 1. Yeah, wait a minute.
I keep saying E, I mean epsilon.
Epsilon, yeah.
Okay, so what I'm going to have to do, and you're going to have to do this, and we're just going to end class right now, is work through this until we get the right thing. So I will work it out myself because I don't have a cheat. I don't have my notebook with me because it's in my office and I know exactly where it is.
That's the worst feeling.
Yeah. But I can't get into the office. I can't. They don't let me go there. 'Cause
Do
you
they
know what
like?
happens. If you walk into a room by yourself that no one else is ever in, you're going to cause all sorts of epidemic.
Do they let Mike in there?
Nope.
Nope.
I mean, you have to get permission to go in there.
Oh, okay.
Whatever.
Do you mind listing the equation one more time, just so I can have it out?
So basically what we're going to do, guys, is we're just going to work on this, and I'll come back with class on Thursday, and we'll see what we can do. I'll make sure that I work on it because I need to do it. And
Yeah.
I'm going to do it with pen and paper, and it's a lot easier for me. So sorry about that. This is
All
a
right.
COVID casualty, but we'll deal with it. And then once you do that, you will eventually get down to something really simple, which is equation 360, which is the way that you actually calculate virtual temperature. So I'll go look at it and see what I can do. But the rest of you guys, we'll just see you on Thursday. Take the extra time to figure it out.
Okay.
Yeah,
All
right.
you can email it. Talk to you later.
Sounds
All right,
good.
bye-bye.
Later.
Take care, Paul.
See you all Thursday.